Okay, so let's start our presentation today. Today we have Edith Newton Wilson. She's the owner of Rock Whisperer LLC. She works to engage emerging professionals in energy solutions for a changing world and consults on renewable energy and climate mitigation projects. Edith is a fellow of the Society of Economic Geologists and the Geological Society of London, a member of the American Geophysical Union, and a founding member of the Geoscience Advisory Board at the University of Arkansas. In 2018-2019, she chaired the ad hoc committee on climate change for the AAPG. She received her BA in geology from Dartmouth College in 1982 and her master's and PhD in carbonate sedimentology from Johns Hopkins University in 1988. Her career in the energy industry began in Houston, where she was an international explorer, negotiator, and manager with Amoco and BP in Oklahoma. Edith worked with Philip Petroleum on Global New Ventures, ConocoPhillips on leadership development, Samson Resources on domestic shale gas projects, and in 2008, she co-founded Tallgrass Energy. Edith has traveled through the Americas, Europe, and Africa, where this is very, very important. She climbed Mount Kilimanjaro in 2004. Amazing. And is conversing in French, Italian, and Portuguese. So now I give the floor to Edith. And let's enjoy this presentation.
Thank you so much. I must mute my telephone. Thank you so much, Stephanie. I'm sorry, it's one of the dangers of working from home. We have the home phone ringing, but it's on mute now. Stephanie, thank you so much. It's a pleasure to be able to speak with you all. I wish you all a good afternoon and give you my apologies in advance that I cannot deliver the presentation in Portuguese or Spanish. But if you'll bear with my English, I've also agreed with Stephanie that you may share the slides, so you'll have material for reference. I would ask only that for the slide material, you use it only for your personal reference and don't distribute it further, as some of the materials are copyrighted from other sources. Also, if any of you would like to continue the conversation after this meeting, please feel free to reach out to me on LinkedIn, where you can also find my email address, or via the Rock Whisperer website, which is at rockwhispererllc.com. And I'd be happy to continue to speak after we start the discussion today. So the first slide that you have in front of you, I understand that we have a number of women on the call, and that's great. The first slide in front of you is, of course, the periodic table, but it also contains a quote from a woman in the mining industry, Lucy Crane, and she always points out at the beginnings of her discussions that as you look around yourself, wherever you are in the world, anything that you see that isn't grown, like wood or food, is mined. So all of us, energy geoscientists, everyone in whatever profession we are in, as we begin to go through this energy transition, we're going to have to become more and more familiar with this periodic table that most of us saw for the last time in our freshman chemistry class. I know that was the case for me before I began to refamiliarize myself. So Stephanie, would you advance this to the next slide, please? Thank you. So today I'm going to be speaking with you about a very specific part of the energy transition, and that is the importance of critical minerals to energy storage and to battery technology. And I'm going to speak specifically also about some changes on the horizon in new battery technology as we get to the end of the talk. The photograph that you see here is from one of the Chilean gold mines. I believe it's an Anglo-American mine. And I've chosen this photo as an introduction because it so beautifully represents this interplay of new and old energy, particularly around the mine. And what you are seeing here is solar panels, photovoltaics, floating on the mine tailings pond. So the reason for that is twofold. First of all, solar energy is at this point cheaper and more efficient and renewable as a source of energy for the mine, but also the floating solar panels act as a barrier to evaporation and reduce the amount of water required in the tailings pond. So there's just a lovely synergy here between mining and renewable energy. And that's what we're going to explore today. So the next slide, please, Stephanie. So I'm going to take us back to what I view as kind of the one best description of what we all do as energy professionals. And this is whether we are working in fossil fuels, or we are working in solar, or we are working in geothermal. We are all working. Through the last century, we have been working to ensure access to affordable, reliable, sustainable, and modern energy for all. Now, this is goal number 7 of the 17 United Nations Sustainable Development Goals. And it is an excellent description of what I was doing in the late 1980s for Amoco. It's also a great description of what I'm doing today and what we're all engaged in. But most importantly, today, so many things have changed about the economics and the availability and the technology of different energy resources that we are now able to focus more readily on the sustainability piece of that. So let's go to the next slide, please, Stephanie. And I'm going to take you through all of the elements of energy resources that we look at as we are engaged in the energy business. Now, whether we're looking for oil and gas or we're looking for renewable resources, there are several common elements that we look for. We look for the abundance of energy. Is there enough? We look at the cost to extract it, and we look at the efficiency of the energy production. Now, this first slide reflects the abundance of energy of all types. And what you see on the right-hand side of the slide in gray are the finite resources for energy in total reserves: coal, uranium, oil, natural gas. Now, we can argue, and you know we do all the time, about these numbers. How much oil is there left in the world? Here, the oil resources, for example, are represented in terawatt years. So they could easily be barrels or joules or whatever. But here we have an estimate of 240 terawatt years of oil left. Now, that number could be twice as much, 500 terawatt years, or half as much, but there still is only a finite amount of total reserve of energy potential in oil, uranium, coal, and natural gas. On the left-hand side of the slide, you see a representation of the amount of renewable resources available each and every year. And in the middle of that big yellow bubble, you see the gray world consumption. Now, these data were put together in 2009, so they're a little bit outdated. In 2009, the globe was consuming about 16 terawatts every year. Now we're up to around 20 terawatts, and we're looking at being at about 25 terawatts before the end of this decade, probably. So if the world consumes 20 terawatts a year and we have 240 terawatt years of oil left, then we have 12 years of oil left. So whatever number we choose to represent those bubbles on the right-hand side of the diagram, they represent a finite amount of time that that energy resource has potential. On the left-hand side of the diagram, in yellow, we could easily envision a scenario where we combine some wind, some hydro, some geothermal, and feed that 16 to 20 terawatts each and every year without running out of those resources. But the big elephant in the room, the 800-pound gorilla, is solar. We're looking at 23,000 terawatts of solar each and every year available for consumption. And this is not all of the solar radiation. This is just the amount of solar radiation filtered for weather, land resources, angle of incidence that is actually available to be consumed. So the message of this slide is really that when we look at abundance of energy resources, the renewable energy resources definitely dominate the availability. Now, there are, of course, other elements that we have to look at. And if you'll move to the next slide, please, Stephanie, we'll look at cost. We all know from those of us who've worked in the fossil fuel business that cost is a critical component. Now, this slide is taken from the annual studies of Lazard, who are a consultant that have been following energy pricing over the past decade. And the timeline is over the last 10 years from 2009 to 2019. And each of these lines represents a different energy resource. And what you can see very plainly here, if you untangle the web of lines, is that solar PV, which is the last bottom box on the right-hand side and is represented by the pale brown curve, if we look at the upper left-hand side of the diagram, solar photovoltaics were almost $400 per kilowatt hour in 2009, and now are less than $40 per kilowatt hour to generate electricity in 10 years. So we have reduced costs for solar an order of magnitude over the last decade. That is a phenomenally fast drop in cost. Now you can see the trends in other costs, including coal, the cost of coal actually rising through the years as environmental risks came to bear. You can see geothermal coming down a little bit, but most importantly, you see that over the last 3 or 4 years, we have actually had wind and solar drop below the cost of natural gas to generate electricity. So now we are sitting in a place in 2020 where the lowest cost of electricity generation on a worldwide basis is sort of in that triumvirate of wind, solar, and natural gas, with solar actually being the lowest cost energy resource for generating electricity. So could we go to the next slide, please? Of course, if solar and wind, because of their low cost, are being adopted more and more to generate electricity worldwide, we have to worry about the times when energy is not being generated but needs to be stored. And what has happened with that in the past, 2 or 3 years is quite phenomenal. The sort of workhorse of the storage energy industry is the lithium ion battery. And these curves show the significant drop in cost on a for rack price of batteries on a per kilowatt hour basis in US dollars on the left. And then the dark blue curve shows increasing capacity of installation of storage. Now, these two curves crossing like this, coming from very high cost and very low utilization to very low cost. If you look at 2019, where the arrow is, very low cost and rapidly rising utilization. This kind of crossing curve scenario is very similar to, it's very indicative of a growth industry. This is what we would have seen in the 1980s in chip technology. We've seen manufacturing capacity gone from 14 gigawatt hours to 285 gigawatt hours, while costs dropped 85% in 9 years. I mean, that is just so fast. That's change in a heartbeat. And we're not really used to that in the fossil fuels industry. This is technology development, and it moves at a really rapid pace. Now, that manufacturing capacity is on track to double to almost a terawatt by 2026. And actually, since this slide was put together just a few months ago, now the same people who are tracking the gigafactories being built are saying we're going to be at 2 terawatt hours by 2028, as you see in the little pink in the upper right. So we have on both the generation and the storage side, this phenomenal drop in cost and improvement in productivity. So on to the next slide, please, Stephanie. So I hope I've convinced you that it's really economics that are driving this, but of course we all know the difference in climate change drivers in greenhouse gas emissions in grams of carbon equivalent per kilowatt hour of electricity generated is also falling rapidly. What you see in this slide are some data from a variety of sources, just comparing the overall on the right total average or median greenhouse gas CO2 equivalency for the various energy resources. And you can see as we go from coal and natural gas at approaching 500 grams of CO2 equivalent, down to, let's say, utility scale solar PV at around 50 grams of CO2 equivalent, we're dropping an order of magnitude in terms of our carbon emissions by going from fossil fuels to renewable energy resources. But there is still some carbon in the system, of course, because we have to build the solar panels, we have to mine the lithium for the batteries. And so those numbers in the pink circle on the left under infrastructure and supply chain indicate how much carbon, what the CO2 equivalency per kilowatt hour generated is just for the materials and the manufacturing and the supply of the elements of all of these renewable resources. So you can see that's where we get that sort of 20 to 60 to 70 average grams CO2 equivalent per kilowatt hour. Still remarkably reduced, but we have to be aware that to produce renewable energy, we still are emitting some carbon. Okay, let's go on to the next slide, please. I want to take a minute here, and we're going to get to the mining picture next, but I want to take just a minute here and zoom out and look at what's going on right now at this moment in time. We know that before all of this happened this spring, we were seeing a growth in the renewable energy and a decline in oil and gas. But when the great pandemic experiment, that I like to call it, totally out of our control, but at least one positive from all of this has been we have really been able to sort of test this transition to clean energy by shutting down our energy consumption the way that we have. And all of these data are from a wonderful report that I highly recommend downloading and reading cover to cover from the International Energy Agency. They just published a report on global energy in April of 2020, and you can access it online. And we can see from these data that our CO2 dropped off dramatically. If you look at the diagram on the lower right, more dramatically than at any time, including the Great Depression, World War II, or the oil shocks of the 1980s. We had this proof in the data that we can transition to a lower carbon world, and that energy usage is one of the major drivers of that. So, so here we have these data that we're able to collect, this experiment that has been conducted through no planning of our own, and we can use those learnings as we go forward. Now, what the IEA is predicting is that the primary energy demand is going to change dramatically with coal, gas, and oil, even nuclear, on the decline in 2020. And the only growth in primary energy demand is going to remain in renewables. So even though there's an overall global decline in energy demand, renewables are still going up in demand. And that's because of that low cost and improving efficiency. So next slide, please. I want to emphasize to everyone that this is not just sort of pie in the sky, oh, we wish this could happen. It's happening in my backyard. The project on the left, NextEra, is putting the largest wind, solar, and storage project ever on the books in the US in Oklahoma, in the western part of Oklahoma, shown in red on that little map. In AES is going to be putting a big renewable project in Brazil, and you can read about that in Energy World. So it's happening in my backyard, it's happening in your backyard, and the evidence is in the projects that are being funded, built, and going online. So let's go ahead to the next one, please. So those big wind solar storage projects are using lithium ion batteries for their storage. The other place that lithium ion batteries are being used, of course, is the rapidly increasing transition to electric vehicles. And what we are now being predicted, each time I read them, the predictions change. The most recent I could find is from Automotive News in January 2020. Even before the decline in travel due to the pandemic. But what they were predicting in January 2020 is that we would be down to only selling about 50% ICE vehicles, that is internal combustion engine vehicles, gasoline run vehicles, by 2030. So a decade from now, we're 50-50 EVs and 50% internal combustion engines. So there's another big consumer of that lithium ion battery. So let's go on to the next slide. So how do these lithium ion batteries work? And I've just shown you, because they have a beautiful diagram in Bloomberg from Tesla, I've just shown you how they work in a car, but it's a similar mechanism to what happens in storing energy for wind and solar. So this is just a diagram showing you that a lithium ion battery is essentially just like the little AA battery that you put in your flashlight or your remote control or whatever, but the lithium ion battery cell we'll talk about a little bit more in a sec. But each of these small cells, about the size of a AA, is packaged together into a module, and then that module is packaged together into a big battery pack weighing a ton, literally just over a ton, with just a small percentage of that actually being lithium and the rest being other metals. And we'll talk about some other metals in a sec. So go ahead to the next slide, and I'm going to introduce you to one of my favorite people, and this is John Goodenough. And John Goodenough lives in Austin, Texas now, but he was born in 1922 in Germany to American parents. John Goodenough is the father of the lithium ion battery. And he is someone that I find his career incredibly inspiring. And the fact that he is at 97, the oldest living Nobel laureate. He was awarded the Nobel in Chemistry in 2019. But anyway, he was born in Germany, schooled at Yale, was a military meteorologist during World War II. He received his PhD in physics from the University of Chicago, was a researcher at MIT, head of the Inorganic Chemistry Lab at Oxford, received the National Medal of Science, the Fermi Award, and of course the Nobel. He was also one of the original team that developed random access memory, or RAM, so a multifaceted individual. He doubled battery capacity using lithium carbonate due to its lightweight and high energy density. And now his group in Austin, he's still doing research at 97 at UT Austin. And now he is working on developing new materials that don't rely on cobalt. And we'll talk about that in a bit. He's also working on solid oxide fuel cells and solid state batteries that use glass electrolytes instead of liquid in an effort to reduce the risk of overheating. So there's John Goodenough on the left, a man to be admired. And on the right is a diagram of a lithium-ion battery. And a lithium-ion battery works fairly simply. If you're an electrochemist, I guess, I had to sort of study it and figure out what was what. But in essence, the anode is on the left and is negatively charged. It's typically made up of graphite. The anode is separated from the cathode, or the positive charge, on the right by a thin porous plastic film through which the liquid electrolyte passes back and forth. So the liquid electrolyte is a carbonate solvent with dissolved lithium salts. While the battery is charging, the lithium ions, positively charged, flow from the positive electrode, the cathode, to the negative electrode through the electrolyte. And at the same time, electrons, negatively charged, flow from the positive side to the negative side along the outer circuit at the top of this diagram. And then the electrons, the lithium ions and electrons combine at the anode and deposit lithium. When the battery is being used or discharging, the ions flow back through the electrolyte from the anode to the cathode, and the electrons flow through the outer circuit to the cathode. So lithium is then deposited at the positive terminal, and back and forth, back and forth. So this is the rechargeable nature of the lithium-ion battery, and it shows you that we're dependent on that fluid electrolyte, but also on the metals that make up the cathode and the anode, and that create that positive and negative impulse for the lithium to move back and forth. So what are those metals? Let's look at the next slide, please. So if we're looking at a lithium-ion battery, and these data are from the World Bank, and I think there's some from Benchmark Lithium as well, we are looking at lithium, cobalt, graphite, and a bunch of other stuff, but those big three at the top are what make up the bulk of that tonnage of weight in that battery in your electric vehicle. And then, as I said, a lot of other metals in smaller quantities, but lithium, cobalt, and graphite are the ones that are anticipated to increase in demand the most due to battery usage. Now, remember, we were talking about carbon emissions from mining activity affecting that supply chain for batteries, for mining in general. 10% of current carbon emissions come from mining activity. So if we increase our mining activity by hundreds of percent, we're increasing our carbon emissions as well. So, just sort of keep that in the back of your mind, that as we see demand for these minerals go up, we also are going to need to worry about how we mine them more sustainably with fewer carbon emissions and still maintain an efficient and cost-effective product. So to make John Goodenough's lithium ion battery, we need lithium, cobalt, graphite. Let's look at a little more detail about where we will get these in the next slide, please. And I'm going to go through each of these maps one by one, but I'm going to show you a series of maps for graphite, lithium, and cobalt. So next slide, please. Let's look first at graphite. Now remember, graphite is the anode material. So actually most of the weight of that battery, most of the volume of that battery is graphite in your Tesla or your Nissan or your in your storage for a wind or solar project. So graphite it's not the sexy one that everybody talks about, but it is kind of the workhorse of the battery world. So what I'm showing you in each of these slides are in the pink dots. Each of those pink dots represents a known occurrence of graphite. Now, it may not be a mine, it may not even be ore grade, but someone somewhere has documented that graphite exists in a deposit for each of those pink dots. And those data come from the USGS professional paper number 1802, which is a global assessment of all of the mineral deposits of the world. So each of those, and these are all available in shapefiles and mappable using ArcMap or ArcGIS. So each of those pink dots then is a deposit of graphite. The countries that are highlighted in shades of pink and red are the countries that actually produce mine graphite. And those data are also from the USGS. And you see the graphite mined production in the gray box on your left. And the main message to take away from this, even though a number of countries are colored as having production of mined graphite, China produces 3/4 or 2/3 of today's mined graphite. Brazil is second behind that, but only just under 10% or just over 10%, followed closely by Canada. So we are also seeing not even on really this map, not even on the radar yet, the Mozambique deposits are probably going to eclipse the China deposits when they actually truly get going. Those mines have just opened up. But remember that we're going to see the global demand for graphite for battery storage alone, just for EVs, is going to grow threefold, 300% by 2023. And each time we relook at these numbers, they get larger and larger. So as the energy transition kind of picks up speed. So here we have graphite mining dominated by China, with Brazil a very, very distant second. Let's go to the next slide, please. And let's look at lithium. Lithium, the same sets of data, the same sources, the same bits and pieces here. We have dots representing lithium deposits. The only thing that is a little bit different is you'll notice the dots have different colors because lithium deposits come in two different kinds. We have hard rock lithium deposits, which are in pink, and we have saline lithium deposits or lithium brines, which are in yellow. And you see the lithium triangle down there on the western coast of South America, all of the yellow dots clustered there between Chile, Argentina, and Bolivia in the salars of the Altiplano. And then you see the biggest producer of lithium is actually producing from hard rock from spodumene in Australia. So note again, lithium anticipated to increase threefold over the next 5 to 6 years. And the production dominated in one country, Australia, about 2/3 of the production, or about 60% of the production, coming from Australian spodumene deposits. And the rest coming largely from the lithium triangle from the brines. Let's go to the next slide, please. I've taken an extra step in looking at lithium to show you how lithium is processed. You see the same color-coded countries that produce the mined lithium, and there's Australia in deep orange with 60% of the mined spodumene. But lithium not only has to be mined, it has to be processed, because remember, and we'll come back to this in a minute, remember that these battery materials, just the concentrated ore from the ground is not enough. We've got to refine it into a bespoke, advanced material, just the right layering, just the right size particle, just the right chemistry in the case of lithium, just the right purity to be used in a particular battery. And each battery is going to define those specs. Each battery manufacturer is going to define those specs a little bit differently. So what this diagram is showing you is not only where lithium is mined, like the last map, but also where it's processed and where batteries are made. Now, the hatchered countries represent where lithium is processed. And only a very little bit of pre-processing is really done in South America and in the US, and a little tiny bit in Poland. Really, the lion's share of the processing is done in China. And then the bubbles representing battery manufacturers themselves, the actual physical manufacturing of the battery components and cells and battery packs, shows that 68% of the batteries are manufactured in China, with the United States a close second, or a distant second, predominantly because of Tesla at about 10%, and the rest of the batteries being manufactured in South Korea, Japan, Poland, and other locations. So I put these two slides in so that you, just to emphasize that it's not just where the materials are mined, it's where they're processed and where the end products are manufactured. So let's look at the next one, which is cobalt. And here in green, you see all the dots representing various cobalt deposits. Lots of cobalt deposits known in South America and Brazil, all over the United States and Canada. But again, if you look at the table on the left, 2/3 of today's mined production of cobalt comes from the Democratic Republic of the Congo in central sub-Saharan Africa, that dark green country in southern Africa. So again, the picture of production is dominated by one country. And as we see demand for cobalt for battery storage alone, which is now essentially 100% of the production of the Congo, and that's expected to triple in a few years. So we can expect to see a strain on these supply chains for lithium, graphite, and cobalt. So now I want to look a little bit at geology. We've been talking about global supply, but I want to dig into cobalt a little bit and go into the DRC. And let's look at the next slide. And I have here a slide reprinted with permission of Mike Porter, who does some beautiful kind of regional and assembly work of all of the different mineral belts around the world. And this is a map showing the Katangan Copper Belt, which is copper cobalt in the DRC. So we are looking at a surface geological map and looking at the cross sections in the lower right as the blocks move along with molten salt and thrust tectonics. You'll see, if you zoom in on some of the very, very fine print, some familiar names of people who've looked at salt tectonics, because they are using the same mapping techniques, the same salt mapping techniques, the same thrust mapping and antecedent normal fault mapping techniques that we've used for years in oil and gas. Same geological principles. Also the same analysis of things like geochemical elements, just sort of different things to look at. For example, in the upper right, you see a figure from Isabel and Mark Barton that was presented at the SEG meeting in Keystone a couple of years ago, where they were differentiating which deposits were richer in cobalt versus being poor in cobalt on the basis of some laboratory work that they were doing. So let's go on to the next slide, and you'll see even more common elements. I've borrowed these figures from Cam McQuaig, who heads up BHP's Center for Excellence in Australia. And BHP is really interesting because they uniquely occupy this position of having both hydrocarbon resources and mineral resources kind of in their DNA. And so what Cam does with his team is look at ways of leveraging what we've done for years in hydrocarbon exploration to the world of mining geology and vice versa. So, for example, they're using a mineral systems approach to looking at critical processes in the diagram on the upper left, where, you know, we might look at regional work, basinal work, and prospect work. On the mining scale, they're looking at sort of new terrain, camp scale work, and again, the prospect work, and analyzing various elements of risk and uncertainty in the same way we look at that in play fairways and prospects. So we're both using resource estimation for asset valuation. We're both using hydrodynamic models and tectonic element mapping, mineralogy, petrophysics, the same sorts of data sets, core, log, well analysis, 3D seismic imaging. I'm going to show you in a slide where that is even beginning to sort of penetrate the mining industry. And there are also a lot of things that are sort of strategic that overlap hydrocarbon exploration and mining. You know, looking at secondary production of some of these minerals, can we get more cobalt out of our existing copper mines that before might have been overlooked? Looking deeper, the miners call it undercover in old basins. There are also in the mining world a large number of very, very small companies that produce prospects, which the majors then buy. So they're also looking at machine learning and AI and focusing on sustainability. So so much in common as we look at what's under the ground, whether it be hydrocarbons or critical minerals. Let's go on to the next one, and I want to show you this example of how seismic is being used in the mining industry. And the diagram on the upper left came from, again, a presentation made by John Ashton in Keystone in 2018. And he showed this seismic line. This is a 2D line of a known mine and a target zone in Ireland in Mississippian carbonates. Well, in Oklahoma, I've been drilling for years in Mississippian carbonates in central Oklahoma. But because in the oil and gas industry, we've got such advanced techniques in processing and acquisition for seismic to better image the reflectors, I showed these lines to John and said, look, and the line on the lower right is through these Mississippian carbonates, essentially the same rocks, but because of our advantage of understanding acquisition and processing more, we're able to see better reflectors and image faults much more clearly in the diagram on the right. So there's a lot of technology transfer that we could do on the seismic side to help in this sort of search for undercover. And the last thing I want to show you on the mining side, if we could go to the next slide, is just a comparison of the investment profile, because there is something very different about a prospect in oil and gas and a prospect in the mining world that doesn't have anything to do with the geology of the host rock, but has a lot to do with the nature of what's being recovered. So this cash flow curve looks at investment versus time, with negative cash flow in red and positive cash flow in green. And this diagram is looking at an example drawn from the Permian. You can see an air photo of the Permian over on the right hand side of the slide. And it's looking at a typical horizontal project where we might have 16 wells on a couple of sections and a fairly back of the envelope calculation of EUR and capital investment. And what you can see is we have a very good return. We have a very high NPV for this sort of typical example well. But what's really unique about the hydrocarbon economic model is the payback comes right out of the bat. This project life is very short, but that well is paid back in the first year, and all of the revenue comes back at you really, really early early days. And this is because of the energy of the oil and gas in the reservoir. This is because you have oil and gas under pressure and easily extractable to the surface, and you have that energy in the reservoir decline in the out years. So you have all of your value in the early years, which is really good from an economic sense. So look at this, we're investing about $175 million, and we have a net PV with a 10% discount rate of about $175 million. And let's contrast that on the next slide with a typical mining example, where we have, again, about a square mile prospect area, as you can see on the right, and a 500-acre mining lease. And just, again, a back of the envelope calculation based on some numbers that were published from a Mexican copper mine. We're looking at an open pit mine making about 5,000 tons a day. The capital investment is very small, only about $20 million, for a net present value discounted at 10% of $150 million. So much better overall return, but look how long we have to wait in this typical mining example for payback, and look how long the project life is. So for investors looking at an investment in energy minerals and critical minerals for storage versus looking at an oil and gas project, the investment criteria, the length of time of the project, very, very different. So even though a lot of the geology is the same, it's important that we recognize that the underpinned investment model is very different. So the last thing I want to tell you about mining and that part of the supply chain in the next slide, before we look at a little bit of battery technology and then we'll finish up, is just remember those slides on lithium. It's not just where we mine the materials, it's what happens all along the way. Mining on the upper left is only a small first step in the life of a critical mineral for energy storage. Then it has to be refined and processed. The cathodes have to be produced, or the anodes have to be produced. Then we have to make the cells and assemble the modules, and finally it goes to the original equipment manufacturer. Graphite on the bottom, I borrowed this slide from my friend Jesse Edmondson. Graphite on the bottom really dramatically illustrates that most of the value is added. There's very little value in a rock with a high graphite content. Even the concentrate has an order of magnitude less value than the final product. So most of the value in graphite and in other critical minerals is added after mining. It's added as we make that advanced material, that bespoke material for the particular batteries. So keep that in mind, because all of this step in the process requires material science, requires mineralogy, requires crystallography, requires a bunch of geological skills that we may or may not have really thought about for some time. So let's look at the next one. And I just want to remind you in this slide that there is still a lot of work being done. There are a lot of different battery types, and those little three-letter acronyms on the slides on the left and right reflect the metals that are in the cathode. For example, LTO, lithium oxide, LFP, lithium fluoride phosphate, LMO, lithium manganese oxide, NMC, nickel, manganese, cadmium. So each of those reflect a different battery chemistry using different metals. And depending upon which metal you're using and how it's configured, we get a difference in the amount of energy that the battery can store per unit volume or per unit mass. So we have a difference in energy density depending on whether we're using nickel cadmium, nickel manganese, lithium ions. And as you can see, lithium ion has kind of won out. It has the highest energy density, more bang for your buck than any of the other battery chemistries, but little changes in that lithium ion chemistry, whether you put cobalt in or you put some other metal in, how it's structured, all of those changes influence where you sit in that orange bubble, in that range of energy density. So there are a number of chemists and engineers and battery tech startups all striving to get to that upper corner of this diagram to have the greatest energy density, the biggest bang for the buck. And I'm going to show you an example from one of those startups in the next slide. This is a little company called 109 Technologies that's actually here in Tulsa, and it's only one of many that are working to achieve better chemistry. And this company has, through proven lab results with nanotech engineering, created a battery material whose composition is still not public information. But next slide, please. If you look at this in terms of energy density, the nickel cadmium batteries were about 750 watt hours per kilogram. There are some startups out there that are looking at working on the graphite and bringing that up to about 1,300 watt hours per kilogram. There's some folks working with silicon, which has some risks and problems with it, but has a higher energy density to get that energy density up to 3,000 watt hours per kilogram. But fossil fuels, oil and gas, have almost 13,000 watt hours per kilogram energy density. That's why they've been such great, you can carry around a lot of energy in a fossil fuel in the tank of your car. Next slide, please. These folks at 109 Tech have created, through nanotechnology, a material that is almost at parity with fossil fuels. So these are the kinds of this is a phenomenal accomplishment and an incredible achievement. And so these are the kinds of advances that are being made by tiny little companies all over the world, changing the chemistry, changing the mineralogy, doing things to the surface, doing things at a nano scale to make things better. Next slide, please. There are batteries out there that are working really well for things like wind and solar farms out in the middle of nowhere. They take up a lot of room. They're not portable at all, but flow batteries that use a redox system instead of that electrolyte to do the ion exchange are great, old school types of batteries. And then there are also, in the next slide, new technology research looking at other ways of storing energy, in this case in a Swedish MIT conglomerate that's looking at using liquid hydrocarbons not to break the hydrogen carbon bond and make energy, but as an energy storage mechanism in and of itself. So the amount of research and the creativity and the ideas that are happening at the front end of battery tech are really just phenomenal. Before we close, I want to come back to, on the next slide, please. I want to come back to something that we talked about at the very beginning, which is, remember, to create clean, affordable, accessible, renewable energy, it requires producing materials. It requires a supply chain, taking, in this case, lithium from the salar in Chile and evaporating it, using a lot of water, using the land in ways that it was not meant to be used. So as geoscientists, we not only have a role in finding the materials, in producing the materials, in processing the materials, but we can also have a role. We can put our hydrology skills to work, our geochemistry skills to work, our environmental science skills to work on all of these supply chains to make them more sustainable from start to finish, to reduce the environmental footprint, to reduce the amount of carbon emitted, to improve the engagement of local communities and how those resources are mined. We haven't even talked about the human aspect of this. But as geoscientists, this is really our role going forward, not just to do the technical extraction, but to engage all the way up and down the supply chain and make it more sustainable. And in the next slide, even at the very end, there's an opportunity. I'm sure many of you have heard the term circular economy. And what we are seeing is that businesses, for business reasons, for profitability reasons, are looking at every aspect of their supply chain, including waste, to extract as much as they can out of it and reuse as much as they can, saving money, saving carbon, saving materials. So what we're going to see is a movement of emphasis from extraction and use and throwing away, or in the case of hydrocarbons, burning up, to a circular economy of extraction, use, reuse, recycle, repurpose, creating value all around the circular economy. Now, before I leave you, and I know you have questions, and I would like to answer as many as I can. I can stay around as long as you want, but I also want to put a couple of other faces. In the next slide, I have for you a couple of friends, Lucy Crane, whose quote you saw at the beginning of this talk, and a friend of mine, Jesse Edmondson. Both of these people can be found on LinkedIn. They're both really excited about people who want to join in looking for critical minerals to drive the energy transition. Lucy works in a lithium stripping project in geothermal wells in Cornwall around old tin mines. And Jesse has started a couple of little exploration companies in the United States looking for critical minerals here where we have lots of deposits but no mines. So both of these people are very entrepreneurial. They both sort of came from a geological background, but they're really engaged in pushing forward the energy transition through exploration for and evaluation of critical minerals. And they're both very cognizant of the need for thinking sustainably about how we do this. And they both would love to hear from any of you if you have questions or you want contacts or connections. Really great. Jesse actually just published an article today about how the southern US is beginning to become a hub for battery manufacturing and what that might mean for the exploration of minerals there. So I'm leaving you in the next slide with something to really think about. And I just want you to think back to that Sustainable Development Goal number 7, finding affordable, reliable, sustainable, and modern energy for all. But in order to really make that economy work, we need to adopt low carbon mining techniques, sustainable development and building practices. And in order for those lithium ion batteries to truly bring us clean energy, we're going to be relying on more innovations in battery designs to improve productivity, continue to drive costs lower, and we're going to see new metals come on demand in those battery supply chains. So as energy geoscientists, I really see our role as ensuring that we develop a supply chain for energy minerals, for battery storage, for these new technologies to really drive that carbon budget to zero and maintain an environmental and social integrity along the supply chain, whether it be exploration, production, processing, or even use of the minerals. So keep that in the back of your mind as you look at whatever element or phase of this new world you plug into. Remember that that it's not just one piece of the supply chain, it's the whole thing. Next slide, please. This is my last little piece of news for you. I'm sure you probably are all already aware that this year, the AAPG Latin America and Caribbean region ran a sustainable development contest. And what you're seeing here are the first, second, third place winners and a little outtake from our awards ceremony. I've given third place pride of place because Rock Whisperer was the sponsor of the third place prize. So I have a particular soft spot in my heart for them. But this contest was fantastic. It was the first year that it had been run, and it enabled young professionals and students to propose a project and get some funding for that project, and then and also some advice on how to complete it. And it's my understanding that this contest will run again next year, possibly at an expanded level. So next and last slide, please, Stephanie. I just love this quotation. Rather than think of this as a challenge of, oh my goodness, how are we going to ever get clean energy all over the world? Instead, I hope that I have convinced you, as my friend Dan Frey says, the world is currently overrun by cheap and plentiful clean energy, and it's up to us to adapt. So thank you so much for your attention. I know we're a few minutes past 5, but as I said, I am here and will stay for any questions as long as you like.
Thank you, Edith, for your amazing presentation. We are now open. If you want, any one of you wants to make questions, you can write. Or as we are few people, you can just open your microphone and make the question by yourself.
Great.
Okay. If anyone wants to just make any question, you are free to do. Okay, I have a question myself. I am currently working on CCS, carbon capture and storage, but associated to shale gas. Now, after this presentation, I have just came to the back of my mind that I haven't seen many projects related to mining, because as you show, there is a high share of CO2 emissions by the mining sector. But do you know if they have any project regarding CCS to abate their CO2 emissions?
Well, it's interesting because the CO2 emissions in mining are very different than the CO2 emissions associated with oil and gas projects. For one thing, CCS is, of course, actually affecting the carbon emissions equation negatively. You're actually putting carbon back in the ground. So, when you are abating, for example, the shale CO2 emissions now, I don't know if that's from the burning of the oil from the shale or flaring of the methane or whatever, but you're actually restoring that carbon. In mining, because they're not either producing hydrocarbons that are going to be burned and emit CO2 or actually emitting methane, most of their carbon emissions come from things like transportation or using electricity in underground processes. So the way that they are mitigating carbon emissions is using all electric vehicles underground, charging those electric vehicles with solar arrays, working on the transportation elements to try to use electric train cars instead of diesel train cars. So it's a little bit different as to how they're tackling their carbon emissions because they kind of have a different source. So I haven't really seen that coupling of CCS and mining in the way that we see it so readily on the oil and gas side. And the other piece, of course, is that our reservoirs that we're producing oil and gas from make great reservoirs to store carbon in, whereas on the mining side, that's a little bit different. Now, there is one example that I think is quite fascinating, which is that, and there's an article that I can send you, Stephanie, that mine tailings can actually be used to store carbon. Because of that affiliation for carbon with certain kinds of silicates. So in some mines, there is this, it's not the traditional CCS like what you're working on, where we're pumping CO2 as a gas into it's more direct capture from the atmosphere into the mine tailings. So I'll send you an article, don't let me forget.
Thank you very much. It was an interesting information. I didn't know about it. And I will clearly dig more on it. So if no one has any questions, I guess we can finish our conversation.
And again, I encourage anyone, please get in touch with me at any time. I know we ran a little over and people have to go, but I'm happy to receive an email at any time from anyone.
Okay, I will be contacting you through our group. And I guess then I see you soon, everybody. I hope you have a good afternoon, evening. Carla is saying, thank you for your presentation. Maria, that is our girls on the energy transition group, is saying, thank you for your presentation. Mariana sent me a message saying that she would like to meet you and talk to you, but she has problems with her audio, so she cannot talk, but she wants to make a question here on the chat.
Okay, great. I'll let you read the question for me because I'm not seeing all the chat.
Okay. Mari, you can make the question, please. She's typing, so it will take.
It's okay. Take your time.
It will take a while. Okay, she already said. Great presentation. She would like to ask if the path of this energy transition will be different in developed and developing countries.
Yeah. Excellent question. And you're probably going to get more of an answer than you bargained for, because this is a real passion of mine. If you think about the economics of installing a small solar panel and a small lithium ion battery and how cheap they are now compared to the economics of bringing a grid to a home and electrifying a whole community, you can rapidly understand that the energy transition, and particularly the proliferation of distributed energy resources, is much more suited to the unelectrified and under-electrified parts of the globe than to try to take a suburban neighborhood in downtown Rio and redo the grid and put solar everywhere. It's much more efficient and economic to start from the ground up in small communities with distributed resources. And so I think personally that the energy transition is going to create a scenario where developing nations actually leapfrog us in technology in the developed world. And I can envision a future where we're sort of left clinging to these old wires hanging around from poles everywhere, wondering what we're going to do with them. It's the same way. I've worked the last few years on a project in Mozambique. When I went to Mozambique for the first time in 2017, everyone had a cell phone. But it was almost impossible to bank in Mozambique in 2017. In order to make a payment, you had to write a check, you had to go to the bank and wait 2 hours. If your ink was the wrong color, it was a problem. In 2018, when I went back a year later, everyone had an M-Pesa SIM card on their phone, and they were making cash transactions, paying their taxes, sending cash to their mom, you know, buying and selling goods with their SIM card on their cell phone on M-Pesa. There will never be another brick and mortar bank probably built in Mozambique. I think the same thing is going to happen with energy. I think we have sort of technologically, we have bypassed the old system of pipelines and wires. You know, the new world is going to be built with distributed energy resources at very low cost, with plug and play components from hardware stores. And, you know, if you go out on Google Earth and you look in very high population density portions of the world, my expectation is outside of the big cities of Rio and Sao Paulo, it's probably the same. I know for a fact outside of Johannesburg and the informal settlements, every little rooftop is getting a solar panel. You'll look and you'll see on Google Earth little flashing solar panels all over those rooftops. Those aren't connected to any big utility. Those are just people with small entrepreneurial businesses bringing energy to their community. So I really think, yes, there's going to be a big difference in how the energy transition takes place in the developed versus the developing world. And I think that the developing world has a distinct advantage that is uniquely suited to the business model of distributed energy resources. So. Sorry, longer answer than you probably expected.
No, very good. We actually enjoy these talks. We always have many long discussions about the energy transition. And the girls, I couldn't keep working with them on this. They are developing an article just trying to understand what is this energy transition path in the developing countries. It's an interesting, very interesting work that they are doing. So when they finish, we will be glad to share with you. We have another question. It's from Juan Camilo. He is from our university too. How do you see the world political conditions for the lithium industry? A few weeks ago, we heard on the news that Elon Musk intervened in the government that took place in Bolivia. Do you think that any group of countries has any advantage in this race? And thank you for the lecture.
Wow. Well, I do have to tell you that I am not very well versed in the politics of lithium in South America, but is it Juan Carlo?
Yes.
Yeah, I would be happy if you would email me to put you in touch with a colleague named Emily Hirsch, who is in Argentina, in Buenos Aires, and she follows the lithium market quite readily. And if you were to follow her on LinkedIn, I believe she had an article about what went on in Bolivia. Certainly Bolivia, Chile, Argentina have a significant role in the current supply chain for lithium batteries. But all of their materials, most of them, at least there's some early processing that's done on site, but most of them go to China for processing. So China still really drives the market there. And I don't know the political wrinkle that you've mentioned, but I'm sure that Emily would. So I'm happy to put you in contact with her to ask that question.
Okay. So Juan, you already know. So somebody else has any question? Okay, I guess no.
Okay.
So, I guess we can then end our presentation. Thank you very much, Edith, for accepting the invitation. We are just a new student chapter here in Sao Paulo. Usually the AAPG community is based on Rio.
Okay.
And Sao Paulo is not known for petroleum, a petroleum background. and we are trying to bring the petroleum industry a little bit of focus to our school for us to increase our sponsorships and help us develop our skills as students. So thank you very much again. You
are very welcome. O prazer o meu. And please, I would love to engage with you in the future. Just let me know anytime you'd like to have a conversation.
Yes, I will. Of course, I will like for us to introduce our other group. It's just girls. We are women in energy, trying to promote energy transition. So yes, you will hear from us.
Great. Oh, that sounds wonderful. I look forward to it, and I wish everyone a lovely evening. And again, thank you so much for inviting me.
Okay, thank you. Thank you, everybody, for assisting us. Bye. Until the next. Bye-bye.
Até logo.
Até logo.